Good afternoon, everybody. Daniele Spiga from INFN, and today I will introduce and shortly highlight the main concept of the both interTwin project with a little focus on the digital twin engine infrastructure. More detail will follow with the two talks that will be given by the two colleagues, Diego and Diana. So these slides summarize at high level the project objectives, the interTwin project objectives. And if you want, the main highlights is that the goal is to go design and implement a prototype of a digital twin engine for many disciplines, so interdisciplinary, and focus to the science, of course. This is based, everything is based on open source, so the platform will be completely adopting open standards, de facto and de jure. And the idea is that this is a playground for developing, co-developing domain-specific digital twins. As you will see, the architecture foreseen specification and the possibility to implement a thematic module and thus to accomplish with a specific community-specific needs. The project foreseen and support several disciplines and use cases, and we can cluster them in mainly two diverse type of use case. On the one side, the physics one, and the other side, the environmental one. You see on the right the two clusters on top of the bottom of the slide, where respectively you can see the environment one and the other side, and on the bottom you can see the physics one. I'm not describing any detail here as we are focusing on the more technical specification. In a nutshell, the benefit of our approach, which is a very modular one, is to increase cross-community development efforts and try to build common frameworks wherever possible in order to maximize the impact and to minimize the sustainability effort. Everything should be and need to be extendable in the sense that need to be able to easily, let's say, plug and play approach in order to extend toward new use cases with respect to the ones that are already part of the project. And about the modularity, I already said everything. So our vision is that we need to provide modules at all the level of the tiered structures, where you can cherry pick whatever, where the user community can cherry pick and choose whatever is needed in order to build the overall use case. So next slide, please. This is the project in numbers. I leave it for future reading, but you can see how many partners are belonging the consortium. There are 30 participants, and you see here how they are distributed in terms of competencies. There are computing capacity providers, technology providers, and obviously there are community experts that need to exploit the infrastructure that have been developed, and the computing capacity that is made available to the consortium itself. And below you see the budget, and you see the time frame in which the project have been developed. And the main concept, the main message here is that we are running the last part, and we are about to close the project in a few months, toward the end of the summer. Next slide, please. So moving to the architecture, I already introduced the main concept, so the modularity and the fact that need to be completely extendable toward new use case and new requirements. And the picture here should highlight what I just said. So starting from the top, you see the applications that are coming from the communities. I told you about the two clusters of communities that we are supporting, and more are coming and might come in the close future. Then you see the thematic modules, where a given community or a cluster of community can develop specific layers and glue, let's say, between the application-specific scientific part, and the infrastructure, the core part of the infrastructure. Soon after this, moving to the bottom of the layers, you see the core modules that are developed centrally, quote unquote, with respect to the community perspective, and those are available in order to be integrated with the thematic one that are accommodating the needs coming from the community. At the very top of the bottom, sorry, of the schema, you see what we are talking about today. So we are actually discussing two main pillars of this architecture, of the infrastructure. And here what I wanted to highlight is that we have two main aspects. On the one side, the middleware, which is represented by the blue boxes, and the hardware, the computing capacity, so the real compute and data storage capacity that is represented by the black boxes. Let me stress since now, and then I will highlight this rather soon, the black boxes should tell you how we are targeting the heterogeneous computing environment. So many diverse providers with different technologies and different way of provisioning resources. Next slide, please. This brings us to highlight how we build infrastructure. So given that we want to cope with highly heterogeneous systems, and you see on the right what does it mean and how our providers are representing a good set of heterogeneity. So we have clouds, ATC and HPC provider. As I was saying, in the left, you see the middleware that either we developed, the orange highlighted names tell you about the brand new things that we developed during the course of the project, and what we cherry picked from the de facto and de jure standard that we have around us in order to enhance coping with our needs. The list of the bolts statement here are a list of main objective of the infrastructure that we developed. So we want to enable the compute continuum, so dealing with highly heterogeneous environment. We want to abstract the heterogeneous infrastructure. This includes even the world-class HPC provided storages. And then, of course, we want to federate, orchestrate, and automate wherever possible the deployment of the services. The core system plus the thematic modules that I told you about a couple of slides ago. Finally, we need to provide all the handles in order to deal with accounting, in order to track who is doing what with the infrastructure that people and the sciences are exploiting. So in the next slide, you see a little bit more of the detail and references to the slightly wider set of middleware toolkits that we made available in our digital twin engine infrastructure. Of course, you see all the details in the URL that is available in the slide, but what I wanted to stress here is that on the one side, we moved toward the second release of the software. So all what I'm highlighting here is included in the second release of the software that is available already. And I want to highlight the different components that take part of our infrastructure. Back to the picture that I shown initially. Those are, if you want, the main components of the blue boxes that were in the bottom part of the architecture. And today you will listen details about some of those and not all of them, because of the sake for the sake of time saving, we need to cherry pick what is the core today. Next slide. A very few highlight on something that is part of the next talk, the concept of federation of the compute part of the highly heterogeneous set of providers that belong the project, but in general the computing environment that we want to deal with. Is the workload offloading. We implemented a way in order to move a step or a piece of a pipeline, a possible pipeline toward the most convenient type of resource that is available in the landscape. So if we want to run a GPU accelerated statistical data analysis step of our pipeline, we can transparently offload this step of the pipeline again toward an HPC center. And today we show you the detail about that. The toolkit that is dealing with it is named Interlink, and detail will come. There is an assumption all of that. We target applications that are running on Kubernetes. So let's say anything that is either cloud native or can be ported to the cloud native approach can be satisfied with this vision. Next slide, please. The next pillar that you will see today with Diana is the data lake implementation that we did. I'm spoiling something that will be detailed shortly. We took existing softwares and we evolved them and we enhanced them toward our needs. What are the needs that the main needs that we want to satisfy? Is basically the possibility to integrate even HPC center in the sense of world-class HPC in the data lake concept that was already existing. And in order to do that, we developed brand new things. You will hear about TPOT, which is the main things that will enable what I just said, and details will come. Next slide, please. A couple of highlights on two more things that are worth to be mentioned here in order to describe the overall architecture. On the one side, we have the policies that we are building in order to extend what is already sort of known, also including very diverse providers. I stress once again that this is one of the key value of our activities is to include diverse type of resources. In terms of accounting, which is another key aspect, we developed and we extended the accounting in order to keep track of the information that comes from Kubernetes. If you got it, Kubernetes is our sort of reference provisioning model in order to provide high-level application, so digital twins, if you want, to the communities. Next slide. Moving toward the conclusion of this introduction, there is also the orchestration and automation of service deployment toward over a cloud's federated system. In this respect, our objective was to make intelligence, in the sense of artificial intelligence, something that was already existing, which is the Indigo Pass orchestration layer. This is a service that take an high-level description of something that you want to automatically deploy on a cloud provider, and we extended toward the capability to cherry pick the most convenient infrastructure where to deploy the high-level service that the user had in mind. To conclude, the picture that you see here, next slide, please, represent where we are today. So we are able to implement a schema like this. On the one side, you see clouds that are orchestrated thanks to the Indigo Pass orchestrator. High-level service are running there. We have the offloading concept that enable the usage of diverse providers in a very transparent manner. Transparent means that the user just see the clouds that are on the left of the slide. And the other side, you see the data lake concept. So somebody that is able to transparently abstract the storage distribution and make the user able to see it as a global file system and move data with one click or something like that. But Diana will tell us where we are and what are the capability of all of that. With this, I conclude the introduction and I leave the floor to the next talk.
All right. So I suppose it's my turn. So let's take from where Daniele left and introducing the concept of offloading. So what do we mean by that? So in synthesis, really bridging all our cloud resources with pretty much anything. So, as mentioned before, the Kubernetes API layer is what we get as an entry point for our frameworks for digital twins. And yeah, we can consider that the entry point for any analysis pipeline. Consider this picture really from 10 kilometers far. And then we want to implement something that allows us to extend the resources of this cluster in a seamless way to any kind of remote resources. That can be either HPC, that is the first point where we started because it was the most compelling use case. You have your Kubernetes cluster, you have an HPC center, a supercomputer running Slurm batch system, and you want to leverage these kind of resources in a most efficient, in a most transparent way from the perspective of the cloud native tools that are used for developing digital twins. And regardless, this tool is used also, is being thought from the beginning with multiple backends in mind. So because this reasoning can apply very well not only to HPC supercomputers, but also, for instance, if you have a VM with a lot of GPUs in your basement, or you have a secondary Kubernetes cluster to manage all your GPUs, or even if you have already a container as a service instance and you want to attach those resources to your Kubernetes cluster. So keep this in mind. It's a pluggable structure, and we will see this in detail just in a minute. What are the use cases from the perspective of the infrastructure, right? So there are two main use cases in mind. The first one is I own both the cloud resources and the HPC resources, so I manage the whole stack. And in this case, I just want to give really access through a Kubernetes interface to my resources. And the other one is, okay, I have multiple Kubernetes clusters managed by people that actually do the digital twin development. And I want to share a common gateway to external resources. So these are the two scenarios, the constraint of our design. And the previous one was what we are targeting. So we ended up basically building a middleware for extending Kubernetes. We gave it a name and we call it interlink. The software in the link, I leave it for reference. That is not anything but a virtual kubelet implementation, so a virtual kubelet provider that implement a set of features that we hope to get for our digital twin engines. So it's designed to be extensible through plugins, and the plugin should be the simplest thing possible that we can imagine. So it's a simple REST API server that can manage the bare minimum requirements for container lifetime. So starting a container, canceling it, getting the logs, and a few more parameters, but not that much. So very simple to provide and to include in any kind of infrastructure. The first design that we had in mind, of course, was, okay, I have this provider on my Kubernetes cluster. I want a virtual node to appear, so some logical entity that allow the users to target a node in a Kubernetes cluster in your cloud. And then the magic happens underneath, so under the hood, if you wish. The Kubernetes cluster will contact this gateway on the remote side, on the edge of your supercomputer, for instance, and will manage through a plugin dedicated to the batch system, for instance, that you want to use, to submit jobs running your container on your supercomputer. Clearly, the communication has to be authenticated between the Kubernetes cluster and the edge node. We have several options for this, and I'm going to through them just in the next slides. All in all, yes, this looks like really a generic adapter for any resource that lives outside your Kubernetes cluster and you want to bring it in for dedicated task. For eventually GPU heavy task or whatever. Now, the implementation that I just presented, we gave it a name like edge node topology, means that you can attach any number of Kubernetes cluster to this gateway, so to the yellow part. And this is pretty handy for a series of different use cases that we have. So for instance, we can think of putting a gateway in front of a supercomputer, and we did, as I will show you in a sec. And this will allow any user authenticated to use the very same gateway with its own Kubernetes cluster. Now, why is not enough? Well, you might need more than this, right? Or you might want more control, or you have different topology. Anyhow, this will remain, for the moment at least, our core implementation. So if you come and want to try, I would really recommend to try this because it's our baseline implementation. This plus the Slurm plugin, that is the first use case that we had in mind, are the most supported and battle-tested implementation that we have. Then there is the in-cluster scenario where everything is running in your Kubernetes cluster, also the plugins and all the logic to be translated. And this is particularly useful if you have a container as a service. So you have Lambda access token and you want to use that, you can use it. Or you have any kind of batch system that is exposed to the public through some kind of authentication. This is also an option. Or eventually, we also had some use cases where a supercomputer like Ulic exposed already a set of API to manage container lifecycle. So we ended up having everything running into a Kubernetes cluster and just calling the remote API through authenticated credentials. That's all. So this is the second scenario and what's for. And the third one is a bit of a mixture of the first two. So we acknowledge that in some cases, also for testing or for very constrained scenario, you have just a login node with no capability to expose external port whatsoever. So you don't have edge access in the very sense of the term. So you can set up everything on your Kubernetes cluster and make the plugin only the part that actually submitting your job running on your login node and communicate with the rest of the cluster through a socket. So these are the three main topology that we validated, and they are working for different kind of use cases. What we lost with this kind of implementation is that at that point, the mapping between the remote resources and the Kubernetes cluster is one-to-one. We lost the capability to attach multiple containers, multiple Kubernetes cluster to the same remote site. All right, so this was the presentation of the use cases and the topology. Now, what I mean by interspace, well, you can consider this phase space for this application. So you have multiple containers, multiple frameworks. Of course, there are many more of these. And you can run all this framework for machine learning, data analytics, whatever, on your Kubernetes cluster because they have already a capability to schedule things on Kubernetes cluster. Then you have different backends, VM with GPUs, HTC, Quantum also, and HPC centers. Okay, so this is our scenario, just like a different view from the previous presented by Daniele, but the concept is the same. So what I mean by seamless, right? I promised you before that the concept under the hood is that we run things that should be as seamless as possible. And actually, this is how you end up to having your Kubernetes cluster. So, oops, sorry. I don't know what happened. Okay, let me run it here in this way. So you have a Kubernetes cluster with a node that looks like any other node. And then you can schedule things like array cluster or any other job that we will see in a minute in a transparent way, right? So you have really Kubernetes native support for pretty much everything. So you schedule this, you install it as you already know and do in any other cloud provider. And the magic happens here. You see the nodes are scheduled on the Vega supercomputer that is providing this capability, and we implemented and test many things on the resources, so it works great. And you see here, so we are logging in into the login node, and we see that, voila, this is the situation. You have pods that are mapped directly to your Slurm job. All the magic that happens in the middle is the responsibility of the interlink implementation. All right, so just quickly, I will show, yeah, that now that everything is running, you have also the capability to get the logs from your pods and that the framework's running just like it was on a normal cloud provider. But you have GPUs running and set up in the Vega supercomputer. Of course, if we go far ahead, you can also submit job to this interface and they will run seamlessly like expected. So yeah, you can uninstall everything and the jobs disappear. Good. So what we did with this technology, what are the use cases that we targeted and what we demonstrated? Well, we start, for instance, from one use case, and we said, all right, let's take a use case for digital twin that was a 3D GAN algorithm developed at CERN, and see if we can submit a training job as a pod and get the results. So, and we did this in two supercomputers, Jülich and Vega, and these are the results. The pod needs just a few changes that are meant to be customized for taking advantage of different flavors of Slurm configurations. So you can pass all the Slurm submit configuration as an annotation in the pod and target nodes through a node selector the particular site you want to run in. So yeah, you see here the whole flow is pretty neat. You submit the pod, it's running as a Slurm job, produce some logs, and then report back the result. The other flow that we followed was to demonstrate that actually any framework running and talking to Kubernetes can do that. And in particular, also enabling in this way event-driven workflows to be executed on demand on the external resources. And this is the case for the pilot exploitation done with Oscar. That is a framework that does actually this: receive a trigger from storage. You can imagine you get new data that you want to do some training on. This will automatically trigger a pipeline and end up in having your result published after some time. And you know nothing about where those stuff run, and it's possibly running on the most available HPC center that you have integrated through Interlink. So you see here in a schema what happens under the hood. The only thing that was required to complete this validation was to attach a virtual node to the cluster where Oscar interface runs, and this will enable the Oscar pipeline to select the node where each subtask of the workflow should be executed. Yeah, you see, it's an elegant way to leverage and exploiting external resources without needing to change anything from Kubernetes upside. All right, then there are other options that actually are not in the pipeline, but are actually a thing already, most of them. There is also the possibility to schedule Jupyter Notebook on external resources. Of course, they are. You can instantiate a Jupyter Hub like you do on your Kubernetes cluster, on your cloud, and then you can configure it to schedule pod on some particular node. It's all it takes from the perspective of the instantiation, and you end up and we end up providing a portal that does just that. Allows you to run on external resources, selecting it from your welcome login page. So this approach started to also to get some community effect in terms of contribution, and we will see in the next slide what are the main ongoing effort to integrate interlink. But we get the messages, we start seeing the community to widen, and so we decided to also apply for contributing to the CNCS sandbox, and we recently joined this group of projects, as you might see in the link, that hopefully will give us also more visibility and strengthening the communities that can access this kind of technology. So it started for our own very specific use case, but it's becoming much more. All right, a few references. We just had last week 2 nice talks happening at KubeCon. One was a flash talk and a collocated event on AI, because of course you can imagine that also more generic and not AI frameworks can leverage the very same kind of technology. And the other one at the main event together with Matteo, talking how the framework developed for AI inside interTwin is talking and closely working with interlink. Now, I do not want to go too much in detail on any of these points, but just to highlight what is currently going on in terms of collaboration. So we plan to have a full-scale or quasi-full-scale Vega supercomputer use case to be tested. So how much we can scale is important. At INFN, we also have several activities to implement this, not only for supercomputers, but also for HTC resources, and to integrating, of course, also the Italian Leonardo supercomputer. Then we had the collaborations that are ongoing. There is the Lysan interferometer that is testing Argo workflows. So again, another Kubernetes cluster, another framework running and talking this lingua franca. And voila, you have another use case that is applying and committing and contributing back to development of this tool. You have then also a capability to offload Kubeflow because, it's again, in the name, it's capable of leveraging anything you can run on Kubernetes. And then some private and enterprise solutions that are also providing some feedback and some utilization, especially concentrated in a way you provide access to your resources. So you might have a distributed infrastructure where you have your own APIs to be used, but users comes and ask for Kubernetes. So this is the case for NewNet. And the other one was a success story where we collaborate with Helix AI, Helix ML, sorry, that is a framework to run developing Gen AI application. And we seamlessly, this was really a few hours work. We implemented the whole workflow of this application, so you can develop your AI leveraging the GPUs in the Vega supercomputer. This was the very, very nice result, and I leave you the link here. So, all right, that's all from my part. Yeah. And I think we can move on, or I don't know. We plan to proceed at this time.
Yes, thank you. We can move now to Diana, and of course, I have the last part for questions. So Diana can share the slides. Okay, thank you. You're muted, Diana, sorry.
Sorry. Okay, so again, I will start with our Federated Data Management components. And our main component is our interTwin data lake, which consists of storage resources across Europe, which here on the map are mapped as small cylinders. Russia, which is the data management layer on top, and FTS that will do the transfer, that does the file transfers. So the way that Russia manages the data lake is it keeps track of three main information, which is one of the storage resources and how to access the storage resource and how to manage individual resource. The data that is stored on the storage resources. So where is the data? What is the size of the data? And things like that. And the users that are allowed to access the data lake. For users that are allowed to access the data lake, all the data in the data lake is available, so public on the data lake level. The system itself is quite flexible. So when user, for example, wants to upload data, it can do so at its local hosted storage element and then use the FTS to transfer the data where it needs, or it can just say, I just want data in the data lake, so I want to upload it anywhere in Europe, and then Russia will choose the storage element that is most convenient. Or for example, it can say somewhere in Germany, and then Russia will again choose. Also, the data can be transferred for only for a specific period of time. So there is some flexibility in how the data is uploaded and travels across the data lake. So that the transfer itself are done using FTS. And what happens is that a user sends a request to Russia where it says, I want this data set at, for example, here shown at Vega. And then Russia will check if the data set already exists at Vega. And if not, it will try to reconcile that request by sending a copy request to FTS, which will then initiate direct transfer between the two storage elements. Here we show transfer from directly from INFN to Vega. It will do so by initiating a pull request from Vega that will try to get data from an IFN, and if that doesn't work, then it will try a push request from here at INFN to Vega. So FTS is a system that is developed by CERN, and they're providing us with a separate instance for our interTwin project, and it's a system that is been around a while and has handled lots and lots of data, and is known to efficiently handle large volumes of file transfers by employing methods like load balances, request queuing, and if a request fails, it will automatically retry it. It also provides us with data logs and real-time monitoring. So this is our basic data lake infrastructure, and the main point of data lake is that we can connect it to our compute resources. So the idea is that users can upload data through the storage facilities at their local storage facilities, but at the end, they want data at computing centers where they can train their machine learning models on them. And that can, in the data lake, it's convenient that at the HPC centers itself, the storage system is mounted to the computing system. So the users at the local site at the site can access the data that is on that storage element, but they can also access any data that is in the data lake by placing transfer rules on them and having them be transferred automatically to that storage element. Some of the storage elements have not, that we wanted to add to the data lake, have not had already were not exposed to the internet via WebDAV, which is important so we can add them to the data lake. For those storages, we developed during the interview project an application that is called TPOT that is very easy to deploy. It's a WebDAV application that supports multi-tenancy, and it's based on Storm WebDAV. So because it supports multi-tenancy, it preserves file ownership, and because of that, is a solution that is suitable for HPC storages. The way that it works is, for example, if another storage edge service sends a request to to storage service that to the storage that has tpod installed. Tpod would accept that request. It would authenticate the user, and then it would use an identity mapping method to discover what is the local username of the user that is being authenticated, and then start a Storm Web Dev server for that user. If another request, the Storm Web Dev server would then deal with the request, and if it's to copy files to the storage element, it will copy the files. If another request comes for that user, the tpod would just transfer it to the same Storm Web Dev, which would then again deal with the request. And if a request comes for a different user, then tpod would again authenticate the user, find what the local username is for that user, and then start a dedicated Storm Web Dev server for that user, to which it will forward the request. After some period of time that the Storm Web Dev servers are inactive, they will be shut down. So for identity mapping, tpod can use a few different methods. One is just a simple file that maps user's federated identity to its local identity. And another more sophisticated method is Alice, which was also developed in the interTwin project by KIT. Alice is a tool for linking a user's federated identity to their facility account. It's an easy to deploy standalone service, and it provides an automated procedure for users of a facility to register the federated identity. For sites, it's very convenient because it also allows them to deploy other services that require OIDC and token-based authentication. So what happens is basically there's a web page that will be available to the users, and they go in and they log into this site with a site account, and then again with their external identity, and they only have to do this once, and then the mapping is done and can be used by services that will be using it. In the data lake itself, the authentication and authorization process is done through the EGI check-in, which is our identity provider. We're using token-based authentication, and to be able to access the data lake, the user has to be a member of a particular VO. For our main development data lake, that VO is dev-intertwin.eu. To access the data lake, there are three main ways the user can access the data lake. One is directly having installed Rusio client on their local machine or a laptop, and that this Rusio client then directly talks to our Rusio server. Be it by authenticated through the client, by using either OIDC agent or just following Rusio's rules, where whenever they input a command to Rusio will, when they first input a command, Rusio will ask them to authenticate and give them a link on which they authenticate, and then they can communicate directly with the data lake with our Rusio server, and can upload data, request transfer rules, or whatever else is done in the data lake. Another way is to access the data lake is through compute resources via Rusio Jupyter Lab extension, and another is automated when the digital twins are running using Interlink and Oscar. So for Rusio Jupyter Lab extension, so basically, Rusio Jupyter Lab extension was developed by CERN in the ESCAPE project, and it enables access to the data lake via Jupyter Lab. So using Interlink that was already presented, a Jupyter session is spawned inside a container on an interTwin compute endpoint. And basically what happens is that you have a Jupyter notebook in a Jupyter Lab like usual, and on the left side there is a part with a Rusio extension where you can browse data that is already in the data lake, set transfer rules to copy data to the local storage element, and you can access the data that is in the data lake on the local storage element through your script. We have also provided, we are providing integration with Oscar, which is open source platform that supports the event-driven serverless computing model for data processing application. It basically manages workflows and triggers workflows. And for the data lake, we have agreed that when user uploads data and then creates a data set, and then when all the data is there and they're not planning to change it anymore, they will close the data set, which will make it immutable. So no changes can be done to the data set. And that closing of a data set will, Rushi will send that event to the RabbitMQ, which is an open source message broker. And then Oscar will trigger a workflow based on that event. So this is how our data lake basically works, all the infrastructure of the data lake and how it's connected to the compute. And on top of that, we have done some changes to support the communities that will be using the data lake. So some communities have some particular problems that needed to be solved. Others already had some data management efforts developed on how to deal with the data, and we wanted to honor that and integrate it into our data lake. So for Virgo, which is a use case behind gravitational wave detector, Virgo interferometer. So Virgo Consortium, which is managing the detector, is storing the detector data in the data lake, and this data is private, which means it should not be accessed by anybody who is not part of Virgo Consortium. As in our main data lake, all the users from all the different use cases can access all the data. We decided to create a separate data lake instance for Virgo to protect their data. Authorization to that data lake is then done based on membership to Virgo interTwin EU VO. So the data lake then consists of a separate Russia instance, again FTS for transferring files, and they have only 2 storage elements per their needs. INFN, where most of the data is located, and then at Vega, where they're targeting to train their digital twins. Another special implementation was for climate change communities, which use stack catalogs, which are spatio-temporal asset catalogs. They use it to describe their data from different satellites, from their simulations. So basically, all of the data they describe with different stack catalogs. Their stack catalogs have quite a different structure than Russia does. For in Russia, we have quite a strict structure, data structure of containers, datasets, and files, where containers can contain other containers and datasets, and datasets can only contain files. In Stack, there's a structure of catalogs, collections, items, and assets, but it's much more flexible. So collections can have in them catalogs and items and assets, but it also can happen that catalogs are containing collections. It can also happen they could have items, but they don't have assets, or they have items at the same level of assets. So we had to agree on a common hierarchy equivalence that would be honored for the data that is in the data, going to be put in the data lake. So some equivalence that is going to be honored. We also added a metadata entry both in Russia and in Stack that show the data, how the data is defined in the other catalog. So for Russia, for a file, we show to which Stack assets it pertains, and for a Stack, we have a metadata entry that shows in which data lake data is and what is the Russia's data identifier for that data. Also, because there are many stack catalogs in Russia, we share the same namespace for particular stack catalog, which in Russia is a scope. Another implementation that we did for climate change communities is we added a public data repository. This is because climate change communities are often using data from public data repositories. And so we register one such repository as a read-only non-deterministic RSC in Russia, read-only because we don't want anybody to write data to the public repository, but and non-deterministic because Russia cannot determine paths by the name of files and scopes as it generally would. So by its standard algorithms, but it has to accept the paths that we give it. And then in that public repository, we only register in Russia's database the data that the use cases will be using. And when that data is registered in Russia, then it can be copied on demand to any storage element where they will be needed. Sorry. And one of the reasons for this exercise was also because it was defined, this data repository had data that was defined by stack catalog. So we exercised our visual stack integration. Another implementation or demonstrations for the climate change community was about the interoperability between interTwin and the STEAM projects. So the STEAM is another European Union project where they working on building digital twins of Earth. So they have a lot of climate data, and some of our use cases are taking part of both projects. So we wanted to show that data can be copied from one data lake to another, so from the destined one to the interTwin data lake, and we have demonstrated that a particular user can get identity to access both data lakes, and then in automated way it can copy data from the STEAM to the STEAM storage element to an interTwin storage element, either directly or via with FTS. To work with Russia, another layer will need to be added that translates the identity needed to access the Russia with identity that needs to access the STEAM data lake. And the final integration for the use case is the one for Lattice QCD. Lattice QCD is one of our physics use cases that are working on building very computationally heavy simulations of lattice for quantum chromodynamics, and the data is managed with an ILDG catalog, which stands for International Lattice Data Grid Catalog. In ILDG covers a lot of Lattice QCD data done in different projects, and most of the data is public, but some of the data is private only for the members of the project for the duration of the project. For that reason, they have developed their own authentication authorization model by using their own Indigo IAM as an identity provider, and they're using a fine-grained authorization model that is based on the scope-based authorization policy. So to honor their solutions, we have implemented a data lake-based solution that is not managed by Russia, since Russia cannot do the fine-grained authorization. And we have allocated the storages at the different sites that are part of the International Lattice data grid, and they're going to use an HPC at SESGA, so we have a storage for them there. And we also implemented we changed a bit the configuration for FTS, so they can also transfer files between different storages while also honoring their fine-grained authorization model. So, in summary, we have implemented a flexible, user-friendly data lake architecture and adopted it to meet the specific needs of the scientific communities involved. And in the interTwin project, we have specifically developed easy-to-deploy services that are TPOT, which is a web dev application that exposes storages for online web dev access while preserving file ownership, and Alice, that is a tool that maps OIDC-based federated identities to local facility accounts. We have integrated Russia with Stack and added a public data repository and explore compatibility with the STEAM for climate change use cases. And we have deployed a dedicated data lake instance to safeguard data from the interferometer. And lastly, we have implemented a solution that honors the ALDG catalogs authentication and authorization model. Thank you. So I assume we're now on the questions part.
Yeah, thanks a lot, Diana. So now we have like some minutes for questions. We're a little bit, late compared to what we planned, but we still have time if you have a question to the speakers, either, in the QA box or just raise your hands and I will let you speak. Any question that you would like to ask? Okay, so I don't see questions now, but you have the contacts of us, so basically you can speak with us via LinkedIn or contact the project or anything. And just wanted to mention that we will have also other webinars for interTwin. Yes, we'll also put it on the slide on the chat. So basically, we are preparing like the next webinar, which will be the 7th of May, about the core modules for interTwin. So we'll have like a longer webinar with 1 hour and a half covering the developments in that area. And again, if you have some question, let us know now. Otherwise, I think I will close the webinar and then we will okay, there's also a post-webinar survey with some questions which you can already fill, and then I will stop recording and I will close the webinar in 2 minutes. Just the time to fill the pool, and then we'll close it.